we were discussing special relativity, and we ran out of time. So there's a couple of items I wanted to talk about at the start of the lecture today before we move on. The first was this big news story that came out a couple weeks ago about the neutrinos that they measured over in Europe at the CERN High Energy Physics Laboratory, and a very timely potential discovery. So that they measured these subatomic particles, neutrinos. We'll talk about those later in the semester when we get to more subatomic physics. But they measure these particles moving faster than the speed of light. We have a name for particles moving faster than the speed of light. They're called tachyons. You also will hear the term superluminal. Okay, greater than light, which means, so that implies that they're moving faster than the speed of light. So last time when we talked about the particles or mass, the energy of any object, we said its mass was equal to gamma, or gamma factor times mc squared. And remember, the gamma factor goes to infinity as the speed of any object approaches the speed of light. Okay? So we said last time that special relativity predicted that it is impossible to accelerate any object with mass either up to the speed of light or beyond the speed of light, because this implies that it would take an infinite amount of energy to get any mass up to that speed. So that limits us to masses that are below the speed of light. So where we didn't quite get last time was, it relates directly to this reported neutrinos moving faster than the speed of light, which is special relativity actually does not prohibit things from moving faster than the speed of light. It just prohibits us from accelerating things to go the speed of light or faster. So if there are masses that are created, so if they're born moving faster than the speed of light to start with, then special relativity says that's perfectly okay, that they can exist. And we call those particles tachyons. Now, the caveat to that is that we've never actually observed anything moving faster than the speed of light. And how something could be created moving faster than the speed of light is unknown. But if there is a mechanism for creating them moving faster than the speed of light to start with, then special relativity does not prohibit them from existing. Now, they have some interesting properties. First off is that once they get beyond the speed of light, the faster they go, the lower their energy is. It actually takes an infinite amount of energy to slow one of those particles below the speed of light. Another interesting factor is that in theory, according to special relativity, if they're moving faster than the speed of light, then their clocks, if we looked at a clock moving on a tachyon, it would be running backwards. So physicists don't like that. That starts to lead to questions of causality and whether we could start traveling backwards in time and stuff. It's great for science fiction, but it questions our job security as physicists when people start bringing up questions like that. So even though special relativity does not says that tachyons can exist, there's actually quite a few particle physics theories, so high energy physics theories, which say that if they did exist, they would be very unstable and could only exist for a very short period of time. So our current theories of physics would say that even though particles its potential to create them moving faster than the speed of light, potentially, I mean, if there is a way of creating them faster than the speed of light, they can exist. They would not exist for more than a brief fraction of a second. And so these results are really interesting coming out of Europe. I think that probably 99% of the physicists around the world think they're wrong, that there's something in the measurement that they will fix. But this isn't the first time that 99% of the physics world has been wrong and that 1% found something really amazing. For example, Einstein, when he created this theory of special relativity, he basically took the assumption that speed of light was a constant in every frame of reference, which 99% of the physicists believed was not true. So we could be wrong, and it could be very interesting results. So, but certainly worth looking into in more detail. But I would not take that into as fact until we see some more data on that. Okay, the second thing about special relativity, which I wanted to, second and last thing I wanted to mention, was the concept of simultaneity. Okay, this is simultaneous, just means events that happen at the same time. Okay? In special relativity, one of the odder predictions is that events that are simultaneous in one frame of reference are not simultaneous in other frame of reference. So the concept of simultaneous events actually is completely dependent on your frame of reference. Okay? And let me give you the example of that, or a common example of that, using our passenger on a train once again. So here's a passenger on the train, which is moving with some speed v. Here's our passenger on the ground, who is watching that train go by. So we've got two frames of reference here. We have the train frame of reference, and we have the ground frame of reference. And let's say that, for the case of argument, that right as this train is passing by the observer on the ground, there are lightning flashes that go off. Okay? This is the common example people use for this. And that there is a lightning flash that strikes the back of the train and a lightning flash that strikes the front of the train. So these are to the ground observer. To the ground observer, you've got a lightning flash here and a lightning flash here that are occurring at equal distances from the two sides. The lightning is flashing, okay, at the two ends of the train, and then the light travels to that observer. Okay? And so to the observer on the ground, those flashes appear simultaneous. That means they appear to that observer on the ground that they happen at exactly the same time. Okay? Lightning flash, there and there. Right? You saw them both at the same time. Now let's think about that observer on the train. So remember, these lightning flashes are emitting light, and they're traveling to the observers. Okay? But for the observer on the ground, that means the light is traveling those equal paths, right? But to the observer on the train, that frame of reference is moving in this direction, okay? Which means that the observer on the train is moving towards that lightning flash, which means that the observer on the train is going to receive the light from that lightning flash before that observer receives the light from the one back here behind them. Okay? So the observer on the train will see the forward flash occurring before the rear one. Okay, so the observer on the train, those two flashes do not appear simultaneous at all. Now, you might think, well, that's nothing fundamental. That's just a trick of the light travel time, that the flashes take a finite amount of time to reach those observers, and the observer on the train is moving to the right. But it's not, because both of those observers know the distance in their frame of reference from where they are to the ends of those trains, and they know exactly how much time it takes for light to travel to them from those two ends, and they're correcting for that in their brains. Okay? So there's a fundamental difference between whether the light reaches this observer on the ground simultaneously and the person on the train, it does not. Okay? In their frame of reference, Okay, these are completely different events. In this frame of reference, those are simultaneous. They see the lightning flashes. They know how long it takes light to travel to them, so they can correct for that. And they know that that flash happened at the same time. This observer would say the exact same thing. They see the flashes. They know how long it takes the light to travel to them. But in that frame of reference, they did not occur at the same time. So simultaneity is something you have to throw out the window with special relativity. Okay. We won't go into the details of this, but this actually does not counter causality. So it doesn't mean that we can alter the cause and effect of different events, which would be cool if we could, but it doesn't. It just means that things look different in two different frames of reference. Okay, so by the way, I know that we're going over special relativity in a lot more detail than we do in the book, so that's okay. This section is just meant to be kind of fun. So I'm not going to quiz you on the midterm completely about special relativity. Okay, so I won't cover it on the midterm any more depth than they do in the book. So this is meant for your guys' general knowledge. Okay, so any questions on relativity before we move on? By the way, you guys are going to discuss this in discussion section probably quite deeply this week, so don't be too freaked out if you got questions. Yeah?
So, like, what is your opinion
On what?
on time travel?
What's my opinion on time travel? Wow, I wish I could discover time travel. I think have you ever heard of Occam's razor? So, which is the easiest answer is most likely true. So, people have come up with very, very elaborate schemes for time travel that involve black holes and wormholes and such. But they're all so extremely elaborate that it's hard to believe they could ever actually occur. So I'm quite a skeptic about time travel. So I don't believe in it. But that said, I hope I'm wrong because that would be really amazing. So, okay, another question? No, everybody knows special relativity. That's awesome. Maybe I will put it back on the midterm. Just a joke, God. Okay, so let's move, yeah.
Is it possible to travel anywhere near the speed of light? Or?
So the question is it possible to travel anywhere near the speed of light? So we have not, you mean as like people to travel near the speed of light? So we have these high energy physics laboratories, right? And in these laboratories, we actually accelerate particles, nuclei, atoms, subatomic particles, up to 99.999% of the speed of light. And so, so there, all these effects of special relativity are just sort of like everyday phenomena, just like walking down the hallway. And so that is very common in physics laboratories. So, but not in the everyday world around us. So we have a little ways to go yet before that becomes commonplace. So, okay. Yes? Yeah. Right. So the question is, if that neutrino observation turns out to be real, that they actually can travel faster than the speed of light, would we be able to use that in any way? So that is a really good question. And I would say we don't know the answer to that because all the accepted theories today, A, predict that they don't exist, and B, if they did exist, that they would exist for, we would never be able to make this measurement. And so, so I would say that there is, in theory, possibility of sending messages backwards in time, interesting stuff like that. But I would say all of our physics theories to date say that that is not possible. So, but we haven't. The thing about those physics theories is, we often extrapolate theories beyond where we've actually measured things in the real world, and there's definitely a prejudice to make our theories agree with what we think the world should look like, and maybe not what it's actually like. And so, who knows? But I'd say right now that the general bias is that is just not a real observation. And if it turns out to be real, then it's really going to fundamentally alter our view of the universe. So it'll keep us employed as physicists for a good long time. So, yep. Okay, so more questions about special relativity. Your GSIs will love to discuss those in sections, right, guys? Yeah, absolutely. So let's move on to talk about fluids. Okay, so we're doing sections 5.1 and a little bit in 5.2. So we'll see how far we get today. We might have to cover some of this at the beginning of next lecture. Okay, so fluids. Fluids you can think about as our masses that do not have a rigid shape. So they're free to change their shape. All the masses we talked about so far are a lot of bouncing balls, a lot of spinning objects have all been rigid objects which had a fixed shape. Fluids are going to be our first example of masses. So you have a mass of water, a mass of air that does not have a fixed shape. That still is subject to all of Newton's laws, but with some different consequences that we need to take into account. So we're going to look at two different types of fluids in general. There's liquids, which generally you can assume are not compressible. And by that we mean that if you squeeze on them, they'll change their shape, but the volume stays constant. They always take up the same amount of space, even if their shape is changing. Okay? That is not strictly true. If you push on a liquid hard enough, you can make it, you can squeeze it down, but it's so infinitesimally small that we can ignore that in all but very extreme cases. So, and of course, the other one is gas. Which is compressible, so the volume can change. We could squeeze gases down into a very small volume. Okay, so in many ways, liquids and gases behave very differently. You're seeing a very vivid example of that outside today while it's raining. So the air is basically staying, it's a fluid, it's staying up in the air, and the rain is falling down. It's a liquid, so they're behaving very differently in the exact same environment. Okay? But there are a lot of common concepts between both liquids and gases that we can share in understanding them both. And the first one we're going to look at is the concept of pressure. Pressure is a force exerted over a surface area of an object. Okay, so let me write this. So pressure is a force exerted over a surface area. Okay, if you take an object and you immerse it in a fluid, like for example, we are immersed in a fluid right now, we're immersed in the atmosphere, which is a fluid of air, then that object is going to feel a force exerting on it from the air or from the fluid in every direction. Okay? And that is what we refer to as the pressure. So let's draw a conceptual picture of this that we'll work with. Let's work with conceptually with a liquid because it's a little bit easier, I think, to think about because it's not compressible. And let's just say we have some container here, like a bucket filled with water. And we're going to take some object, like a little cube, and we're going to immerse it down inside of that bucket. Okay. Then, so we would claim this fluid has a pressure. And if we take our little cube here, okay, so there's our little cube. That little cube has little surface area A on each side. Okay. So the fact that that cube is being immersed in a fluid means that fluid is exerting a force on it in every single direction. That's the pressure. So if we draw the force on here, there would be a force acting on every single face of this object. Okay. And that force is equal to the pressure times the area. Okay. So the pressure is pushing that object to the left, okay, but there is the opposing pressure on the other side, which is pushing it back to the right. Okay. There's another pressure that's pushing it upwards on the bottom face, but there's an opposing force, the pressure pushing it downwards on the top face. Okay. So there's equal pressure on each of those faces. So let's do a couple notes about this. Okay, the first is that the force due to the pressure always acts perpendicularly to the surface. Okay, we have a name for that. We've already seen it's a normal force. Okay, so each of those forces exerted by that pressure is acting and perpendicular to the surface that it's acting on. Okay? And the second, which is not so conceptually so conceptually obvious, is that the fluid exerts pressure equally in all directions. There is a pressure on that object, and the direction of the force is determined by the surfaces of the object, okay? Not because there is a preferential direction of the pressure. That pressure is pushing in all directions, okay? The resulting force has a direction, and it has a direction determined by the normal for the surface, but the pressure itself is acting equally in all directions. So let's do a couple examples of that. The first is a demo called, these are called Magdeburg spheres or hemispheres. And here I just have this little cast iron sphere that's been cut in half. Okay. You can see that it's very easy for me to pull these apart. Okay. Not a problem. The reason, well, you might, if you don't think about it, it might seem obvious that this is easy for me to pull this apart. But when you realize that there's air pressure in this room from the atmosphere above us exerting a force in every direction, it might not be so obvious because the pressure is pushing inwards on both sides of this. Okay? But because this has been open to the air, there's opposing pressure on the insides of the spheres pushing outwards. So all the pressure forces are balanced on this, okay? And there's no net force from the pressure acting on this. Okay? Just like when you're sitting there, you're not suddenly accelerating in one direction or the other because the pressure is exerting force on you in all directions, even though we're so used to it, we actually don't really notice it. Okay, so now I'm going to hook this up to a vacuum pump, and I am going to pull that air out of there. So if I can get this on there. Okay, so let me run this for a second. Okay, so I have just sucked almost all the air out of this thing. Okay? So now there's no pressure on the inside of it, okay, or it's negligible. Okay, we just have the atmospheric pressure on the outside. And I cannot pull this apart. You guys can attest I'm a pretty strong guy, right? Yeah. As hard as I pull, I cannot get these apart. Okay, so let me, you want to try? Okay, don't twist them, just pull on them, okay? So you can see I'm not faking. It's pretty hard, right? Yeah, okay. So let's just estimate what is the force of the atmosphere pushing on these things that makes it so hard for me to pull them apart. And just to, if I break the vacuum, so I let air in, okay, you can see that they pop right apart. Okay, so those, let's just put some numbers up here. You guys are sitting at the bottom of a fluid. That fluid is the atmosphere, the air that's acting on you. Atmospheric pressure. Okay, it is at sea level 1.0 times 10 to the fifth newtons per meter squared. Okay, if you're used to newtons, okay, a lot of people unfortunately still think in terms of pounds. That is 15 pounds per square inch. That is the pressure acting on every single square inch of your body as you're sitting there. There is 15 pounds pushing on you continuously. Okay? We don't notice it because it's pushing in every direction, so those forces are all balanced on us. Okay, but they're all pushing inwards, normal to us. That sphere is about 2 inches in diameter, in radius. Okay, so if we draw a picture of it, here's that hemisphere. Okay, there is, it's got about 2 inches in radius there. There is a force of pressure pushing those two hemispheres together because I have sucked out the air on the inside. Okay. So that's just atmospheric pressure. Then the atmospheric pressure, the force due to atmospheric pressure is going to be about the atmospheric pressure times the area it's working on. Remember, pressure is a force per unit area. So that area is pi times that radius squared, which is 2 inches. And if you plug in that and the fact that it's 15 pounds per square inch, that's about 190 pounds. Okay. So there is 190 pounds. Yes? Nope, it's pi r squared. It's just the cross-sectional area. So it's pi r squared. So there is about 190 pounds pushing that right hemisphere into the left one, and about 190 pounds pushing that left one into the right one. Okay, so I don't know how much I can bench press, but it's not 380 pounds. So that's why I'm not able to pull those apart when the vacuum is in there. Now, one thing you might have saw when I was walking around was that pressure does not have a direction. Okay? The resulting forces have a direction, but pressure itself does not have a direction. So it didn't matter if I was trying to pull them apart in this direction or trying to pull them apart up and down. Okay? Pressure was always pushing them back towards each other, pushing them together, okay? Independent of the orientation that I was holding them. Okay? So pressure itself does not have a direction. The resulting forces from the pressure does have a direction, and it's determined by the surface area and which direction normal to the surface area is. Okay, so let's do a little bit more dramatic example of that. Have a gas can. I'm going to suck the air out of this. Okay, so suddenly it doesn't have any pressure on the inside, countering the pressure that's pushing on it from the outside. And so there is going to be 15 pounds per square inch pushing on every single surface of it inwards, and no pressure pushing back outwards. Okay. There's a lot of force acting on that. Okay, so that's what happens if you emptied your lungs. So don't breathe. No, just kidding. Okay, so a lot of pressure acting at the bottom of our atmosphere because we're all sitting immersed in this fluid. Okay, so let's add a couple more concepts that are common to all fluids, liquids, and gases. So pressure is one. The next one is density. Density is easy. It's just mass per unit volume. So a density of the fluid is just equal to the mass divided by the amount of volume that it takes up. Okay. Once again, for liquid, this density is constant, or we can treat it as constant. It's nearly constant, so we can change the shape of it, but we're not changing the volume of the liquid for a given mass. Okay? For gases, that's different. So giving gas a different amount of mass, different mass of gas, okay? When we press on it, we can compress it, so we can change its volume, which means we can change its density. So for liquids, you could take density as being a constant, and for gases, you have to be a little bit more careful in your treatment of those because it can change. Okay, the second concept, which is common to all, is that the pressure will increase the deeper you go in a fluid. And this, by deeper, we're implying there's a gravitational field, and we're going deeper in the fluid in the direction that gravity is pointing. Okay, so that is due to the weight of the fluid above. Okay? The pressure here at the bottom of our atmosphere is much larger than it is if you go up, 10 kilometers or 100 kilometers, which will put you in orbit, because of the weight of the fluid above it. So let's derive that a little bit. Okay, so let's draw our container of liquid once again. So you can consider this as just being like a bucket of water or a swimming pool or Pacific Ocean. Okay? And let's just look at the pressure as a function of depth in this fluid. What we want to do is, let's think of this as having all the fluid at rest. Okay, let's think about what we mean by fluid at rest. So none of that fluid is moving, it's just sitting there. Okay, everything's perfectly still. If it's at rest, that means that all the forces are balanced. There's nothing accelerating, there's nothing moving. Okay, so all the forces acting within that liquid are balancing each other. Okay, let's think about what forces are acting. And to do that, let's define a given depth. So here's our depth in that fluid. We're going to look at the pressure at this level. And let's conceptually think about what's going on there in terms of forces. Okay? There is a pressure here, which is what we wanted to find. And that pressure is arising because all of the fluid below this level is supporting the weight of all the fluid above it. Okay? So let's forget for a second this is a liquid, and let's just think about it in terms of two masses. We've got the liquid above that point, and we've got the liquid below that point. So for all that liquid above it, let's just say there is a mass. It's at rest. Okay? That liquid, or that mass, has a weight. Its weight is just mass times the gravitational acceleration, pulling it downwards. Okay? That means that there must be a normal force, which is being provided by the liquid below it, which is holding it up, right? So there's a normal force, which is just being provided by the liquid below, which is keeping it up, because it's at rest, right? It's not moving. So those forces have to be balanced on it. So we still have masses, they still have weight. It's at rest, which means there must be another force balancing that. Pretty easy. So we know that these two forces have to be equal. Okay? So now let's say that this has some area, cross-sectional area that we're looking at there. Then we know that this normal force, what is providing it? Okay? It has to be provided by the pressure. Okay? It's the pressure at this depth, okay, which is providing that normal force, a support force. Okay, so we've got two forces here. We know that the normal force is just the pressure at that depth times the area, okay, the cross-sectional area of that container we're looking at. Remember, pressure is a force per unit area, so the net force at this point is going to be the pressure times the area across that container, which is pushing upwards. And that has to balance the weight of that liquid above it. Okay, the weight is just going to be equal to the mass times our gravitational acceleration, g. Okay, the mass is equal to the density times the volume. Remember, the density is the mass per unit volume. So if we multiply the density times the volume, then we get the mass. Okay? And then one more step, because we want to know how the pressure changes with depth. Okay? When we're talking about volume, we're talking about the volume of that upper liquid, okay? The liquid above this depth that we're looking at. So the volume of that is just going to be the area of our container multiplied by the depth, okay? The depth of the fluid we're looking in. So this volume here is just the depth times the area. So we can write the weight is going to be equal to the density times the area times the depth, and then finally times little g. Okay, so we've got two forces. We've got the normal force pushing upwards, which is just the pressure times the area, and we've got the weight of the fluid above it, which is just the density times the volume, area times depth times g. And these are balanced because it's not accelerating, which means that this force is equal to this force. Okay? So let's go ahead and see what happens when we set those equal to each other. When we do that, we're going to get a result which we conceptually understand very easily. So if we set those equal to each other, we get pressure times area. That's the normal force pushing upwards. That's going to be equal to the weight, which is the density times the area times the depth times our gravitational acceleration. And something really surprising happens here. Okay, there's one part of this which is really conceptually easy and one which is just a little bit strange, which is that area cancels out on the two sides. So, and I'll talk why that's strange here in a second. So this tells us that the pressure is equal to the density of the fluid times the depth times little g. That is a pressure as a function of depth in the fluid. So that is telling us two really important things. First off, which I think is pretty conceptually easy, is that the pressure increases the deeper we go in the fluid. So the further you go down, right, the deeper we go, the pressure has to be bigger, and the pressure has to be bigger because it has to support more weight of fluid above it. Right? So the deeper we go, the larger the pressure is. Okay? Of course, if you've ever done any scuba diving or any type of diving, this is really obvious. Okay? The pressure increases as you go deeper. If you've ever, actually, if you've ever hiked to the top of a mountain, you know the opposite, which is the pressure gets lower as you go less deep, so go higher in the atmosphere. So the pressure is a linear function of the depth, okay, for fluid, for liquid. Okay, so the pressure is, actually there's a few things that are important here. Another is that the pressure is a constant at any given depth. Okay? So the pressure is the same on the right side as it is on the left side. Okay? Even though it's increasing as we're going down, at any given depth, the pressure is a constant along here. Okay? And then the last thing is that the pressure didn't depend on the area. Okay? The reason that's strange is we could have drawn any shape we wanted to of container. So we drew this nice little square container here. But we could have drew any shape we wanted to, and the area would have canceled out, which means that our derivation does not depend on the shape of the container whatsoever. So to draw a really dramatic example of that, let's say we have a bunch of different shapes of containers. Okay, so here's one that, like the one we just drew. Okay. We're going to look at the pressure at some depth in that one. Let's compare it to some other shapes of containers. We could have had a cone-shaped, maybe a fancy vase here. Here's the water level. If we looked at the pressure as a function of depth, it is exactly the same as in that one. It does not depend on the fact that that thing's getting narrower as it goes down. Pressure does not depend on the cross-sectional area of the vessel at all. Okay? So it would be the same if we had a beaker-shaped vessel. Or I'm going to draw one really strange one, which we will come back to in just a second. If we had a funny shaped vessel like this, which was filled with fluid, okay? So it has this skinny little pipe sticking up here and this bigger one over here. Okay? And if we looked at the pressure at that depth, they're exactly the same. Okay? The pressure is a function of depth. It does not depend at all on what the shape of the container is. Okay? So it also means it doesn't depend on whether you're swimming in a little tiny kid's pool or a great big giant pool. If you're at the same depth, you're going to feel the same pressure, okay, regardless of how big the vessel is containing the water. So let's keep this one up here because we're going to come back to this one in 1 second after we introduce one more concept, which is Pascal's law. Okay, Pascal's law asks, what happens if you push down on the top of this fluid? Okay? So let's say we had a raft or some sort of plunger on the top of this, and we push down on it. So we're introducing an additional pressure on the top of this fluid. Okay? So Pascal's law tells us that that pressure will be passed on to the rest of the fluid everywhere. Okay? So it increases the pressure everywhere in that fluid, not just at the top. So if you introduce a pressure, you push down on that fluid, you're increasing the pressure at the top of it, and it's going to spread equally throughout the entire volume. Okay, so let me write that down and then draw a picture of it. So pressure applied to an enclosed liquid is conveyed undiminished to every part of the fluid. Okay, and the surfaces of the container. Okay, another example of this is if you take like a 2-liter soda bottle, right? And you keep the cap on, okay, and you squeeze it. Okay, if you squeeze that, you're increasing the pressure on the sides, okay? But that pressure is being distributed throughout the whole thing. So if you squeeze it hard enough, right, it's probably going to blow the lid off because that's going to be the easiest place for that pressure to be relieved, okay? But the fact that you're introducing a pressure anywhere in the fluid means it's going to get spread out throughout the fluid, as long as it's an enclosed container. If it's able to squirt out, that's a different story. But as long as it's enclosed, then that pressure will get transmitted throughout the fluid equally. So I'll draw another little picture of that. So let's say we have our container of a fluid, water, some sort of fluid, and let's put a little plunger on the top here. So you can just think of that as like a little flat platform or a plunger, like a plunger in your toilet, and we introduce a force on that. So we're going to push it down. So we're going to push. So we introduce a pressure. Okay, and Pascal's law tells us that that pressure gets transported everywhere in that fluid. And once again, the pressure is not a directional thing, so the pressure is directed anywhere. Okay, so that pressure will increase the force against the bottom of that container as well as against the sides of the container equally. Okay. So, very practical example of this uses a container just like this one over here we already drew. Okay, and that is hydraulics. This is how hydraulics work. Let me draw a picture using that same vessel over there. Okay? And that'll help us understand how hydraulics work often in heavy machinery like forklifts and stuff like that. Okay, so here is our vessel that contains some liquid, water or oil, I think is often used in hydraulics. Okay? And the idea is pretty simple behind that. There's 2 halves to this vessel. They're connected at the bottom, so that means that there is a common pressure for any given depth between these 2 fluids. Okay? And they're open at the top. We're going to add plungers on there, but they have different areas. So let me call the area of this one, the little side, little a, and the area of the bigger side, big A, just to differentiate the little side from the big side. Okay, and the idea behind hydraulics is amazingly simple, which is you're going to use this Pascal's law in order to multiply a force that you're applying on an object. Okay? So the idea is simple. We're going to introduce a little plunger on this side. Okay? And we're going to take that plunger and we're just going to push down on it. So we're going to push down on it with some force. Let me call it little f, because that's the force that we're applying, which is a relatively small force. Okay? If we push down on that, then remember this liquid is not compressible. Okay? So if we push down on that side, and this stays at rest, so let's say there's another, we're going to add a big plunger over here as well. Okay? If we push down on that side, then there's going to be a resulting force pushing upwards, balancing it, but that force is coming from the pressure at that point. So there's some pressure at that point. And that pressure at the top is just equal to the little force that we're applying times the area, because it's balancing it. Okay, so we're going to push down on that side, okay, and the liquid's going to push back up on it, and they're balanced, and so that means the pressure times the area of that little side of the cylinder is just equal to the force that we're applying to keep it balanced. Okay, so that's assuming this thing doesn't go squirting out, okay? And the reason it doesn't squirt out is because we got this other side over here where we've got some, let's say we've got some big heavy mass sitting on top of that we're trying to lift, okay? So the fact that we're introducing a force on this side means that we are introducing a pressure in this system, okay? And that pressure gets distributed uniformly throughout that whole volume of the gas. So that means that the pressure we introduce here is also being introduced from Pascal's law over here. So we have a pressure on this side, which is now pushing up on the plunger on the right. Okay? So it's exerting a force, and I'm going to call this big F. And that force is, sorry, this is F over A, isn't it? That's force per unit area. Thought something looked a little funny there. So that's the pressure that we're introducing. This force is just the pressure that we've introduced at that depth times the cross-sectional area of this side, right? So if we plug that back in here, okay, we just see that well, two ways of thinking about this. One way of thinking about this is that the pressure on these two faces are equal. Okay? So the pressure on the left side is our little interforce we've introduced divided by the area. That has to be equal to the pressure on this side from Pascal's law, which is what we call big F over the area of the right-hand side. Okay? So if we rearrange this, we see that the force that this is exerting on the right-hand side is just equal to the ratio of the areas times the little force that we introduced. Okay? That means if we push down on this little cylinder, okay, the resulting force on the right hand of the cylinder, the bigger cylinder, has been multiplied by the ratio of the areas of the two sides. So, which means that we've multiplied the amount of force that we've exerted. And so this is a very useful tool if you're trying to create very large forces, which is how hydraulics work. And so let's do a demo of that. Here is a hydraulic jack. This is just like the jack you use to maybe to change the tires in your car, to lift up your car. And if you look very closely, let's see, can you zoom in on this? Okay. Yep, if you look very closely, you'll see that there are two cylinders here. There's a big cylinder, which is backwards from the way I drew it there, but there's a big cylinder on this side, and there's a little cylinder over here. And the way this works is that there's just a common fluid that these are sharing, and there's little plungers that go down. Okay. So that means if I push down on this side, okay, the force that this side exerts gets multiplied by the ratio of this area of the big cylinder to the area of the little cylinder. Okay, so let's, let me turn this around so you can see. I'm going to start exerting my force on that little area. See that right now the force that I'm exerting is just going into lifting up the big cylinder on the left, but let me get it up here close. What we got here now is a piece of wood that is now hitting against these stops up here. Okay, this is probably closer to what I drew over there. So now I'm going to start exerting a force downwards, and this big cylinder is going to be exerting the multiplied force upwards. Okay? So you can hear that wood starting to break. Okay? I'm not exerting a very big force on this, okay? But it's getting multiplied by the ratio of those cylinders. Okay? And that's how the hydraulics work, by just using that very simple fact that pressure gets distributed throughout the fluid in order to multiply the force that's being exerted in those cylinders. Okay, so where are we at on time? Okay, so any questions so far about pressure, density? Yeah. Okay, yeah, that's a great question. So, so her question is, when pressure is being applied to a fluid, then work is being done. And we saw a very dramatic example of that here. And so you might, this is another case where you might think we're somehow violating basic laws of energy, like work and energy, right? Because if I just tried to break this, there's no way I would be able to do that on my own. Right? But you notice, remember that work is a force multiplied by a displacement. And when this was up here, well, you can even see it if I'm pumping here, right? So as I start doing this, my little force is acting through a very large displacement, right? So whereas this thing barely moves at all. So the fact that I multiplied the force on this side means that the displacement is much smaller. So I'm not violating conservation of energy, okay? I'm just doing a little force over a very long distance, okay? And so it's multiplying the force, okay? And then, but it acts over a very small displacement. That'll work, right? Great. So yeah, so we're not violating any energy conservation here, but we're definitely doing work by exerting those forces over a displacement. Good question. Yes? Multiplying the force means that the force on this side has to be much larger than the force on this side in order to exert, in order to have the same pressure. Okay? So the pressures are equal. They're being distributed. The pressure is being distributed equally. So the pressure at this point is the same as the pressure at this point. But remember, the force is the pressure times the area, and so the fact that this has a much larger area, pressure times area. So the fact that this has a larger area means that the force is much bigger. So we're exerting this little force, and it's getting multiplied by the ratio of the areas, and so the resulting force on this side is much larger. So that's what I mean by multiplying the area. Does that make sense? Yeah. Okay. So we're just we're using this little trick with the pressures in order to take a little force that we can exert and turn it into a very large force, which is useful for lifting heavy things and breaking stuff. Okay, so any other questions? Okay, so let's talk a little bit about buoyancy. Okay, we all know from experience that objects that are submerged in, for example, water or submerged in any fluid will feel lighter. They'll feel like they weigh less than objects that are just in air, right? So, and you yourself, if you go in a swimming pool, you will feel lighter than you do if you're just outside. Okay? And that comes from what we call buoyancy. Buoyancy is just a type of force. And it results very naturally from the fact that pressure increases as a function of depth when you're in a fluid. Okay, buoyancy. Buoyancy in everyday terms just means that objects seem lighter. Okay, seem lighter, that means they appear to weigh less in water or in any other fluid than in air. Okay. And we also know that if objects have a density less than water, that they will float. Okay, so that means that the liquid, or the fluid, in this case water, is exerting an upwards force on the objects that are in it, because they have to be balancing the weight of the object. So if the parent weight feels lighter, okay, than the actual weight, then it has to be having some normal force acting on it. Okay, so the buoyant force. Very easy. Let's show an example of this. So I got two masses here. One of these is aluminum, I think, and the other one is brass. So they have different densities. Okay. But let's see, it's on, right? This is just measuring their mass, okay, between the two of them. So you can see they have equal masses. Obviously, this one is much denser than this one. So let me start submerging this, and let's see what happens to the mass as we do that. So I'm going to submerge it by basically just lifting up this beaker of water. Make sure I'm on the right channel here, which I am not. Let me switch this back. There we go. Okay, so now I'm going to start submerging this by lifting it up, I think. Wow, I think I broke this. Let's see if the other one works. I'm making it heavier. Wow. This is better than faster than light travel. Okay. Bad demo. I just proved that things get heavier when they get submerged in fluids. Wow. Please don't do any press releases on this till we verify. Okay, so ignore this. Let's just go back to the board, shall we? Okay. I think that's intuitively obvious. We know this from experience that when you put objects in water that they appear to be lighter. Okay. This is actually very easily explained quantitatively by Archimedes' principle. Okay. Archimedes' principle, which has allowed us to build basically ships since even back in the Greek times. Okay, so Archimedes' principle basically just says when an object is immersed into a fluid, like when we put these masses down into a fluid, the fluid exerts an upwards force or buoyance force on that object, which is equal to the weight of the fluid that that object displaces. So let me write that down and I'll draw a picture of that, which will hopefully make that a little bit easier to digest. Okay. When an object is immersed in a fluid. The fluid exerts an upward force on the object. This is what we call the buoyant force. And that upwards force is equal to the weight of the water or the fluid displaced, the weight of the fluid displaced. Okay, so that means if I take an object this big, okay, and I put it down into, let's say, water or in a pool, it's going to feel an upwards force that's the same as the weight of that amount of water, the same amount of water that, the amount of water that would take up the same volume as the object that we immersed. Let's draw a picture of this, which gives us a fairly simple conceptual proof of this idea. Okay, so let's start off with our container of fluid once again. So this could be our pool, Pacific Ocean, drinking glass, and let's say that we've got our little object here that we're going to immerse inside that. So it's got a volume, it's got a mass. So what we want to imagine is, let's pick out a volume of water which is identical to that, to the shape and size of that. So here is our little volume of water that is identical to that object. Okay. So now, let's think about that volume of water. So that volume of water has a weight that's pulling it downwards. Okay. So let's treat that as just a solid mass that's sitting there at rest. Okay. And since it's at rest, that means the weight of that water is being countered by a buoyant force pushing it upwards. Okay. We know that's just the result of the pressure acting around this object. So the fact that the pressure is greater at the bottom side of this object than the top of the side of the object means there's a net force upwards. Okay. Or in other words, that the water below that object, that mass, is being supported by the pressure below it. Okay. That's the buoyant force. Now, let's just pretend like we're doing this experiment on Star Trek. Okay. And we're just going to teleport out this chunk of water and teleport in that mass. Okay. And when we do that, we're left with this situation, okay, where that mass has replaced that water, okay, but we haven't changed anything else about that whole situation. So the pressures are still the same on all the surfaces. Okay. So that means the resulting forces are all the same, okay, which means that that object is going to feel the same buoyant force pushing it upwards that this equal amount of water, equal shape of water, felt when it was sitting here at rest. Okay? So the force that that object feels is the same as the water that it displaced, okay, when we put it in there. Okay? So that tells us exactly what the buoyant force is on it. Okay? So that object, of course, has its own weight that is pulling it downwards. So we know intuitively, right, that in this case, the weight of that water was balanced by the buoyant force. Okay? So if we come over to this case, okay, if the weight of that object was more than the amount of water, okay, that we displaced, then its weight is going to be greater than the buoyant force, and it's going to sink. And if its weight is less than the weight of the water, okay, then it's, the force of gravity downwards on it is going to be less than that buoyant force, and it's going to start rising. Okay. So the buoyant force doesn't change. The buoyant force is just the amount of force supporting this equal amount of water over here. Okay. But the weight might change depending on the density. Okay. So the mass of this object, if its density is larger than the fluid, so larger than water in this case, that means its mass is greater, its weight is greater, and it's going to start sinking. And if its density is less than water, then its net weight is less than the amount of water that it displaced, which means the buoyant force is greater, and it's going to start rising. Okay, so let's write that down. So for objects that are denser than water, we're going to have that their weight is greater than the buoyant force. And so they're going to start accelerating downwards. There's a net force on them, unbalanced force on them. So they're going to sink. And if the, for objects less dense, in water, we're going to have the weight is going to be less than the buoyant force. And so these objects are going to start rising when after they're immersed in that fluid. Okay, so there is a special case of this for objects that are less dense than water. Okay, we know that if an object, if you take an object less dense than water and you submerge it in a fluid, it's going to start rising. Okay? And then once it gets to the surface, it's going to float on the surface. Okay, so floating is a special case of the buoyant force. Let me draw a picture of that. So first off, you only get objects floating if they're less dense. Otherwise, their the increased weight is going to have them sinking towards the bottom. Okay, so here's a surface. Here's our object that's floating on that surface. We've got two densities here. We've got the object mass per unit volume, or the object density. We also have the fluid, in this case water. Okay. Now, if an object's just floating there and it's sitting there at rest, then we know that the buoyant force is balanced with the weight of the object. Okay. And the only way that can happen is if it's not displacing its full volume, right? If we push this all the way down so it was completely submerged, we know that the buoyant force would be larger than the weight and it would increase. I mean, it would move upwards. Okay. So it's not displacing its full volume, it's only displacing a fraction of its volume. Okay. And there's an easy formula for that. Which is that the fraction submerged, so the fraction of the volume submerged, is just equal to the ratio of those densities. So it's the object density over the fluid density. And that's pretty easy to prove if you feel like writing down a couple lines, equations. But conceptually, that makes sense because we only need to submerge the fraction of the volume, okay, that counters the weight of the object. Okay? And if we submerge any more than that, it's going to feel a net force, buoyant force upwards, which is greater than its weight, and it's going to start rising. Okay, so one example of that is our icebergs. Okay, so salt water has a density of 1,025 kilograms per cubic meters. Ice has a density of 917 kilograms per cubic meter. So if you look at ice or an iceberg floating in the ocean, then the fraction submerged is 917, the density of the ice, over the density of the fluid. Which is 89.5%. Okay? So that's why if you're out on the ocean in a boat and you're getting close to an iceberg, you don't want to. You want to stay far away because you're only seeing 10% of it. Okay? The other 90% is submerged below the ocean. And that's why so many ships get into accidents around icebergs, because conceptually they see the iceberg off in the distance and they don't realize that they're missing 90% of the mass of that ice, okay, which could be much closer than the 10% you're seeing poking up above the surface of the water. Okay, so we will finish up with fluids at the start of our next lecture. And we're moving on to heat and temperature. So we're starting to go very quickly through a number of different topics. So be sure to keep up with your reading, guys.